For lecture number 5 of thermodynamics, let's continue talking about a first law analysis for steady flow devices, so open devices. Lecture number 4, we addressed the first three categories: nozzles and diffusers, compressors and pumps, and turbines. Since compressors and turbines are so similar, I only worked an example or a turbine out of these two. Later I will work an example with compressors and pumps. We did work an example with nozzles and diffusers last time as well. So let's consider the last two categories in lecture number 5. Heat exchangers and mixing chambers are effectively heat exchangers and throttling devices, and we'll work an example of each of those. And if there's any time left, I may go back and work some more examples up here. Otherwise, I'll just save that for lecture number 6, which I will record this weekend. Okay, so heat exchangers. The purpose of a heat exchanger is to change the temperature. We find the page. Change the temperature of the working fluid. So heat exchangers are actually quite simple devices. They're not intended to do any work on the working fluid or have the work or take any energy out of the working fluid to perform work. The sole purpose is to either increase or decrease the temperature of the working fluid. So all they are is a pipe, basically, and the outside of the pipe is exposed to a different temperature than the fluid is at. So if the surrounding temperature is very, very hot, we can heat the fluid. If the surrounding temperature is cold, we can cool the fluid down. So flow comes in. I draw it as a box with squiggles through the middle. This is just to suggest there's a long, complicated, tortuous, maybe we would say, flow path as the fluid moves through a long piping network. And the whole point of the piping network is to then increase the area for which the fluid is then exposed to the temperature outside. There's no reason for the pressure to change, except that in a real fluid there is a viscous flow resistance. So it actually does take a pressure to be higher at 1 than 2 for there even to be a flow to push through. But from a thermodynamic state standpoint, that pressure change is negligible. So we will assume, at least in the ideal case, unless you're given the pressure drop, we will assume that the pressure is the same throughout the heat exchanger. So P2 is equal to P1 in this case. There is no work mechanism, so no W dot. We only have heat transfer. So another type of heat exchanger might be to consider the heat transfer between two different working fluids. So you might have an enclosure that's actually insulated, but you might deliver a hot fluid, call this fluid A, that enters and leaves, and then you might deliver a cold fluid, fluid B, that enters and leaves over here. And the idea is for the system, is to have a lot of exposure between these two fluids internally. Right, so this pipe has to be close to that pipe. Now the fluids are not mixing in this case. This is still two different pipe systems. They're just close to each other. So the idea is to encourage or promote there to be heat transfer from the hot fluid to the cold fluid. Therefore, fluid B comes in cool, and it comes out a little bit warmer. Actually, I have it drawn the other way. Fluid, if you come in at state 3, cold, it gets heat. It will heat up a little bit from the heat transfer from the hot fluid A before it leaves. Or maybe your goal is to cool down the hot fluid A coming in before it leaves over here. Either way, both actions are occurring in this. So if you do, so you can do a energy balance analysis. Consider a first law just on this, right? Just like you would analyze this one. Or you can analyze just fluid B just like we would analyze that one. Or we could actually consider the entire unit combined that has 1, 2, 3, 4 ports on it that's actually insulated. The heat transfer would be internal in that case. Those are heat exchangers. Another effective heat exchanger would be a mixing chamber. So a mixing chamber would be delivering hot and cold fluid. The hot may even be steam, and maybe this is water. Mix those two together so you're delivering a warm fluid in that case. So in this case, the fluids are actually mixing together. Up here, the piping is separate. Um, so again, ideally in a mixing chamber, we would expect, at least from a thermodynamic state standpoint, the pressures at 1, 2, and 3 are all the same here, unless this happened to be some complicated diffuser slash heat exchanger, and in which case they would have to give you the temperature drop. So if they don't give us any information about, sorry, the pressure drop, if they don't give us any information about the pressure, we are to assume in all heat exchangers that the pressure is uniform throughout the devices. I will point out up here though, in this particular type of heat exchanger, the pressure can be different between the fluids because they're not connected, but the pressure at 1 and at 2 will be the same, and the pressure at 3 and at 4 will be the same for the same ductwork or piping work. Okay, so typically no mechanism, there's nothing to do work here. The goal is to promote the heat transfer, although that might sometimes be internal. We're almost always neglecting potential energy. In fact, in this class, we will always neglect potential energy here. For kinetic energy, that is very often negligible, especially if they don't give you any information about that. The only way kinetic energy would be significant would be if there is a phase change due to the temperature. The temperature is caused to change. If that causes there to be a phase change, then the density would be so much different for a vapor compared to the liquid, that then conservation of mass would dictate a significant velocity change. Okay, so ideal case, no pressure drop across the pipes. Okay, so let's work an example of a mixing chamber. So simple, very practical situation is to take hot water and mix it with cold water to produce warm water. We're going to assume that the pressure, or they give us a pressure at 20 psi, and the chamber is well insulated. The hot water enters at 140 degrees Fahrenheit and the cold water at 50 degrees Fahrenheit. So we want to determine what is the ratio of the mass flow rates at the inlet. So what's the ratio of the hot and cold mass flow rates that will produce an exit temperature of 110 degrees Fahrenheit. Okay, so I'm going to draw my mixing chamber as, I'm going to draw two ports first, one for the hot and one for the cold. And then the exit is a single exit on the other side of the mixing chamber. So this is a rigid, effective chamber, so there is no boundary work going on in that. No wires crossing the boundary, no shaft. We're not stirring this in any way. This is location 1, this is 2. So at this location, let's call this the hot. So T1 is equal to 140 degrees Fahrenheit. T2 is the cold, that's 50 degrees Fahrenheit, and then we're delivering over here at state 3, T3 is equal to 110 degrees Fahrenheit. So there's an M dot, let's call this M dot 1 at that location, M dot 2 at that location. Over here at this location is M dot 3. Conservation of mass would be pretty trivial, right? M dot 3 has to equal M dot 1 plus M dot 2. So there's a connection between those, but the question is, what does the ratio of, what does it say, the hot water enters to determine the required ratio of the inlet mass flow rates to produce. So it's not specifying which one to provide. So I'm gonna declare it as, we're looking for M1 relative to M2. Find M1 relative to M2 to provide T3 equal to 110 degrees Fahrenheit. So my first thought would be, well, if this is 140 and this is 150, wouldn't just this just be the average of these two? Um, well, actually, you could do a weighted average of these two, and it's going to be really, really close to that answer, believe it or not. So 110, let's see, the average of 50 and 140 is, let's see, 190 divided by 2. Sorry, that would be, yeah, 190 divided by 2. So what does that equal? What is that? 90. The average between the 190 divided by 2. Why can't I do that? That's going to be 95. So it's not the 110. So we would expect there would have to be, since this is above that, there would have to be a little bit more M1 compared to M2. So let's go through and do an analysis, try to figure out what that has to be from a thermodynamic standpoint. So conservation of mass we've effectively already done, but I'm going to write it down anyway. Conservation of mass, summation of m dot n minus the summation of m dot exit is equal to 0 because we're in steady state. There is two exits in this case, so two inlets in this case, and one exit. So m dot 1 plus m dot 2 minus m dot 3 is left to equal 0. Okay, so that's where we already came up with a logical explanation up above. Now let's write down the first law. That will also give us a constraint for this problem. Summation of m dot n, h plus 1/2 the velocity squared plus gz minus the summation of m dot exit, h plus 1/2 the velocity squared plus gz plus q dot minus w dot is equal to 0. Because it's in steady state. We're going to the kinetic energy change and the potential energy change we are neglecting. Neglecting delta kinetic energy and delta potential energy. We're assuming there's not a phase change. We're not given information about the cross-sectional areas or velocities anywhere, so we couldn't include that if we wanted to. That will likely be negligible for this device. This is not intended to be a nozzle or diffuser. Potential energy is effectively always negligible for these small devices. At the end there's two inlets again, and then there's one exit. The entire mixing chamber is insulated, and there is no mechanism for work. So we're left with m dot 1 times h1, one of the inlets, plus m dot 2 times h2, the second inlet, minus m dot 3 times h3, there's the exit out of these terms, and everything else is 0 in the equation. So now we're left with these two equations. It turns out that we have a temperature at each of the states, and a pressure. I did not write that down above. Let's go back up here, add the pressure. P1 equals P2 equals P3. That's all at 20 psi. The states are defined, so go back down to this analysis. We can do some work. We can come up with numbers for all of those H values. So between these two, what we're looking for is the ratio. We need to somehow do some algebraic manipulations to find m dot 1 over m dot 2. So what I did is I decided to use this equation to eliminate m dot 3, and then out of the equation that's left, divide by m dot 2. Alright, so I substituted right there. M dot 3 is actually m dot 1 plus m dot 2 with the above constraint, and then divide. So let's go ahead and substitute m dot 1 h1 plus m dot 2 h2 minus, put m dot 1 H3 minus m dot 2 H3 to account for both of these and place there. That's equal to 0. Okay, so now take that equation and divide that by m dot 2. So now we'll end up with m dot 1 over m dot 2 H1 plus H2 minus m dot 1 over m dot 2 times H3 minus H3 equals 0. This is the unknown that we're looking for in the problem. So m dot 1 over m dot 2, take these two to the other side of the equation, right? Factor this out, so divide by h1 minus h2. So the final answer is h3 minus h2 divided by h1 minus h3. Right, and all these states are defined, so now we just need to do some work to come up with the number of values for those states, and we can substitute. Okay, so they're all compressed liquids. So state 1, H1, is going to be equal to HF, well, they're all for a compressed liquid going to be equal to HF plus BF, P minus P saturation in each case. So let's put a note up here. All three states are compressed liquids. So we're going to evaluate it this way. Unless P, the pressure, is much, much higher than P saturation, this is going to be a small term. Remember that BF for a liquid is a small number. So typically this is negligible unless that pressure is very, very large. Here our pressure is 20 psi, so it's almost it's just a little bit more than atmospheric pressure, so that's probably going to be negligible. I'm going to write out anyway what HF at T1 is. HF at T1 is 107.96 BTUs per pound mass. If I have to evaluate these two, those additional ones, I would need a BF. So BF at T1 is 0.01629 cubic foot per pound mass, and then a P saturation at T1 is 2.8, excuse me, 2.892 psi. So those are the numbers I would need to evaluate this formula for location 1. Go get those numbers for T2. I end up with 18.06 BTUs per pound mass. VF at T2 is 0.01602 cubic foot per pound mass. P saturation at T2 is 0.178 psi, so a very small number. Continuing on, we need HF at T3 is 78.02 BTUs per pound mass. VF at T3 is 0.01617, and P saturation at T3 is 1.276 psi. Okay, so if we now compute each one of these, H1 is equal to the end result. I'm using this formula up above, HF plus the end result of computing this, paying attention to units to put this correctly in BTUs per pound mass. This ends up equaling the 107.96 plus the adjustment is 0.05157. Final units of that are a BTU per pound mass. The adjustment is very small. H2 comes out to be 18.06 plus 0.05876. BTUs per pound mass. H3 is 78.02 plus 0.05458 BTUs per pound mass. So these are the numbers, the end result of that we would substitute into our answer. If you remember, m.1 over m.2 was equal to H3 minus H2 divided by H1 minus H3. This comes out to be 2.0. So we need twice as much hot water as cold water in order to achieve our 110 degrees. But notice that if we take these values and substitute into this formula, we're evaluating H3 minus H2 here. So this minus that. These numbers are effectively canceling. The adjustments are canceling. The same thing here, H1 minus H2, since both of these are compressed liquids, when we take the difference between these two, H3 minus H1, those two cancel. So it is very accurate to say that this is approximately equal to HF at T3 minus HF at T2 divided by HF at T1 minus HF at T3. That still comes out to be 2.0. So these adjustments are small to begin with, so there's already a decision: is the work necessary to compute that worth it? And the answer is yes, so long as that P is large. Typically 20 psi is not enough. You see that was in the fourth decimal place here, fifth decimal place of the information that's given here. Not really significant actually to conclude in H itself. But when we're evaluating a difference, additionally, we're evaluating a difference between the two. Now these already small effects are canceling anyway. So it's okay to do this, make this assumption. What I'd like you to do, though, is show me that you understand that equation. So put that on the test and then cross that out, declare that you are neglecting that. Okay, so let's now talk about throttle valves, the last section. So for a throttle is a device that is trying to restrict the flow and causes a huge reduction in the pressure. So it's just a valve imagine a valve that you just crack open and you just bleed a little bit of flow passing through this. Then this would have to be at location 1. This would have to be very, very high pressure relative to 2 to have a significant flow rate. So P2 will be much, much less than P1 for a throttle. Imagine another way to do a throttle is to just block the flow and then put a pinhole in the middle of the plug that's blocking the flow, and we're just allowing a little bit of flow to pass through. That's as complicated as the device is. There's nothing going on here, no moving parts, no electrical wires or anything crossing the boundary, not even a lot of surface area for heat transfer, so there's no mechanism for power. Negligible heat transfer, so typically we'll say it's adiabatic unless they give you information on that. Potential energy, always negligible. Kinetic energy, typically negligible unless that huge pressure drop causes there to be a phase change. If that pressure drops so much that this now turns into a vapor at the exit, now the velocity could be significantly higher at the exit than at the inlet because the cross-sectional area is effectively the same. Okay, so if we go through an energy balance with all of those assumptions we've made above, neglecting kinetic and potential energy and Q and W, the only thing that's left in the equation is H. So in an ideal throttle, H2 is equal to H1. Ideally, a throttle is a constant enthalpy device. H2 equals H1. And so you can, in general, make the assumption, if they don't tell you differently, that this is an ideal throttle, so just assume a constant enthalpy device and use this. You can't then, just remember, you can't then also do an energy balance, because this is the result of an energy balance. This is an energy balance for an ideal throttle. There's some of the details to go through, reducing the fact that an ideal throttle is a constant enthalpy. Right, here's the advection terms. I'm neglecting potential energy first. Negligible heat transfer, no mechanism for power. It's steady state, so that side is gone. So we have this to begin with, and then if we also neglect the kinetic energy, there's also no phase change to worry about. We can neglect the potential energy. So the ideal case is H2 equals H1. That's all that's left of the energy equation. If you have to deal with a phase change, well, then now you just need to apply conservation of mass, and you have to have information about the cross-sectional areas in the state so that you can figure out what the velocities are. Right? You're familiar with conservation of mass. Okay, so let's work an example. Here's a steam turbine, actually. It's operated at steady state under part load by throttling the steam that's coming into the turbine before it enters the turbine. So before throttling, the pressure and temperature provided are 200 psi, 600 degrees Fahrenheit. After throttling, the pressure is dropped down to 125 psi. At the turbine exit, the steam is at 1 psi, so the pressure is dropped tremendously and the quality is at 90%. Heat transfer with the surroundings and all kinetic and potential energy effects may be neglected. So they're actually telling us what can be neglected there. That's nice. They want us to find then the temperature at the exit of the turbine, and also the power developed by the turbine in BTUs per pound mass. So the power per unit mass flowing through the turbine. Okay, so we have a turbine. So I'm going to draw a turbine first. And so we have flow coming into the turbine. And then, but the inlet is actually throttled, so I'm going to put the throttle valve here as well. And it's steam is passing through the turbine. The turbine is a device that's going to produce some power. So let's identify this as state 1 coming into the throttle. State 2 is the exit to the throttle and then the inlet to the turbine. State 3 is the exit to the turbine. Okay, so now let's get the information they provide to us where we can see it. P1, the pressure coming in to the throttle, 200 psi. The temperature coming into the throttle is 600 degrees Fahrenheit. At state 2, we know the pressure drops. P2 is equal to 125 psi. They don't give us any more information at state 2, and then at state 3, they tell us that the pressure at 3 has dropped all the way down to 1 psi, and that the quality is 90%. So the quality is equal to 0.9. So state 1 is defined. State 2 is defined. It's asking us to find the temperature. Oh, sorry, not at the turbine exit, but at the turbine inlet. So we need to find T2, and then also the power developed per unit mass. And also, that would be little w defined as W dot divided by M dot. Okay, so we only have one property at state 2, so to find T2, we need something else to help define the state at T2. Well, if this is an ideal throttle, then H1 equals H2, and state 1 is defined. Alright, okay, so to find T2 for an ideal throttle, H1 is equal to H2. Alright, then H2 and P2 define state 2, so that's what we can use to find the temperature at 2. Okay, so this is superheated steam, superheated vapor entering 200 psi, 600 degrees Fahrenheit. H1 is 1321.8 BTUs per pound mass. Alright, so that's also H2. So H2 is equal to this, and the pressure at 2 is equal to 125 psi. That's still superheated. If we go to the superheated tables, with that information, we'll find out that temperature T2 is equal to 589.22 degrees Fahrenheit. So there's the throttle part of this example. Right? This is the result of an energy balance. This is the first law for the throttle. Okay, so next is asking for the power per unit mass. So now we need to do a first law analysis of the turbine. First law of turbine. Summation of m dot n h 1/2 the velocity squared plus gz minus the summation of m dot exit h plus 1/2 the velocity squared plus gz plus q dot minus w dot equals 0. Okay, don't throw this away. This is the goal of the device. Do we have any information about Q? Let's look back up. We have a steam turbine operating at part load. It's throttled. The pressure, turbine exit, steam quality, heat transfer is negligible. It says heat transfer with the surroundings and all kinetic and potential energy effects are negligible, right? Right, so that's negligible. That's given. Kinetic and potential energy effects, it says, are negligible. There's one inlet and one exit. So m dot 1 h1 minus m dot at the exit is, oh, that's the m dot 2 h2 in this case. M dot 3 h3 is at the exit, minus w dot is equal to 0. That's all that's left in our energy balance. Conservation of mass, right, we'll say m dot 2 equals m dot 3. Actually, we could even put m dot 1 in there, equals m dot 1. Alright, so there's just a single m dot in this problem. This is by conservation of mass. So we can factor out our single m dot and divide that. That allows us to evaluate the power per unit mass without actually knowing the mass flow rate. So divide that by m dot. Take this equation and now divide that by the m dot. That'll turn our w dot into a little w. So we'll end up with an equation that says w, take that to the other side, it becomes positive, is equal, which is defined as w dot over m dot is equal to h2 minus h3. So now we just need to figure out from the properties at state 3, that state is defined. It turns out that h3 is 1001.76 BTUs per pound mass. H2 we've already figured out is H1, so our final answer is W is equal to 320.04 BTUs per pound mass. So for every pound mass of steam that flows through that unit, through the throttle and the turbine, there are 320 BTUs of energy generated through the rotating shaft. I want to also point out for this example that we could have, go back here and look at our device, we could have performed an energy analysis of the entire steam and throttle unit. So the inlet is 1 and the exit is 3. Right? This would be internal, so it would not show up in that case in our energy balance. We would still have a single stream, so we have the same conservation of mass result, but now the power in the end ends up equaling H3 minus H1. Notice that you get the same answer because H2 happens to be equal to H1 in this case. So you still get the same amount, get the same answer, whichever one you analyze. So quite often in these problems, you'll have a choice as to what you want to perform your energy analysis of. And then you just have to keep track, if I'm just going to look at parts at a time, how the two parts interact. Okay, so I'm going to go ahead and conclude this lecture with those two examples, and I'm going to record another lecture then that will start working some of your homework problems that have been assigned and addressing some of the issues that come up in those. And in those examples, I will make sure I work a compressor and a pump example. So this concludes lecture number 5, and lecture number 6 will be created today as well.